So really, without further ado, I'll move on to tonight's talk, which is entitled Modelling and Engineering COVID Digital Contact Tracing. In some ways, contact tracing was the gold standard of the way people coped with infectious diseases and the like. So it'll be interesting to see the development of the digital side of things. So without further ado, I'd like to introduce Rob Hinch and Adam Fowler, and they can tell you all about it.
Thank you. Okay, so our talk is only roughly 2 halves, well, me and Adam. So we worked together. Well, we came at this from 2 different places. So I am an infectious disease modeler, or it's newly one at the start of the academic. So I'm going to talk a little bit about SARS-CoV-2, a bit about that epidemiology, and what we do in epidemiological modeling, the questions we're interested in, and our use of computers as well. And then we'll go on to, then Adam will talk specifically about how the apps were actually written for the phone. So how digital contact tracing was actually implemented on people's phones in the real system, as opposed to my part is going to be more looking at the epidemiological part of it. So as I said, I'll start talking a little bit about SARS-CoV-2, just to remind everyone what happened very early on. And then I'm mainly going to talk about epidemic control measures and epidemiological modeling. So the type of things that we want to use modeling to try and understand. And then I'll go and talk about digital contact tracing, why we thought it was a good idea, and how we got it. After that, Adam will talk about the engineering side of things and about Bluetooth and how to make things work with the platform. So, very quickly, in case anyone's forgotten, I'm sure they haven't, how did SARS-CoV-2 start? Well, with all epidemics, what tends to happen is all novel pathogens, they get found because there's a cluster of unexplained cases of some disease or some symptoms in a hospital somewhere in the world. And this happened to be in Wuhan, and there's a lot of people had pneumonia there, and no one could work out why they were getting this pneumonia. And at the end of 2019, they had 27 cases within the hospital, but nobody had died at the end of 2019. But they were very concerned because there were these people getting severely ill. No one knew why. That tends to be how many.
Very sorry to interrupt. The remote people can't really hear because of there's an echo of the microphone. With you, this you will learn that I'm changing. Oops. Can I just come back to your previous slide, your after slide?
Let me try and test. Is that better? Any echoes now, or it's good?
It's better.
It's better. Okay. So where was I? Yes. So there was 27 cases, but no deaths. But people were very concerned there in China. At that point, it was what happens is that things are then get reported to public health authorities. So at the time in England, it would have been PHE. In China, they had Chinese Centre for Disease Control, and then WHO, the World Health Organization, was informed almost straight away. But by the end of 2019, everyone had been informed, and the Chinese scientists moved very quickly, and they'd isolated the virus, and they had sequenced it, and they had the genetic data for it, which was shared globally back on the 10th of January 2020. So probably before anyone here had heard of COVID, the genetic sequence was already found for the virus. It'd been published, and that allowed people to develop tests for it and allow for the vaccines to be developed. And a lot of the pharmaceutical compounds for the vaccines were developed back in January and February 2020. So what then happened? Well, suddenly there was very rapid growth in Wuhan, and there was also spread in China, and people started to die. And obviously, no, it was very bad. However, the Chinese stamped down on it very quickly, and they managed to get it all under control by the end of February. So the Chinese were very successful at preventing the spread of it. However, a few cases got out and got to the rest of the world. And what then happened? As we know, it sort of spread globally very quickly. Very quickly, every country in the world effectively had it. By the end of March 2020, 50,000 people had died of it worldwide. And as we all know, in March 26th, we went into our first lockdown. So what I'm talking about here and the work that we did, and we started working on it in probably end of February 2020. So before the first lockdown, and everything was really done between February to April, May 2020. So that is that period, so just before lockdown and June that first lockdown. So you have a new epidemic. How is it controlled? And there's loads of different ways epidemics are controlled, and it all depends upon what method works. Depends upon what the way that it's spread. So the mode of transmission is really important. So certain things like HIV and a lot of STDs, they can be controlled by essentially educating people about exactly how transmission occurs, and then people can change their behavior. So HIV and monkeypox were controlled in the UK and in Europe and the US as well, really by education. Remember in the early 80s, we had all these big education campaigns and adverts in television. So that was how they were controlled to a reasonable degree. And the second thing, and I guess is maybe the gold standard for which we control infectious diseases, is vaccination. So obviously smallpox, polio, we both controlled and effectively eradicated. Smallpox was eradicated, but then we still are vaccinated for measles and mumps, and while they're not, and that sort of controls it and prevents us from having large outbreaks of them. If an infectious disease is transmitted by insects, for example, they're the vector, then environmental changes often happen. So the way malaria or yellow fever being controlled a lot has often been around controlling insects. That may be controlling where they breed, but also controlling your own environment, so mosquito nets and things like that. You then get on to contact tracing. Contact tracing is in many ways the go-to thing which are used by public health authorities when a new disease, this new infectious disease is discovered. And that essentially works by someone interviewing the person, someone who's been confirmed as a case, and then finding out who they've been in contact with, and going and talking to them and advising them to get tested and things like that, and certain measures to help them to try and prevent spread on from those people. Then for a lot of respiratory diseases, mask wearing is incredibly effective. And this is probably one big difference between us here and Asia. The original SARS outbreak in 2003, which was predominantly in Hong Kong and a little bit in China as well, didn't spread that far beyond that. But one way that was controlled then was by a lot of people they started wearing masks, and it became part of the culture in many Asian countries to wear masks to prevent respiratory diseases to be spread. So that was very important for the original SARS, but I think it's also been very important for SARS-CoV-2 as well. And then we get on to sort of more drastic measures like border controls, isolating cities, isolating countries, and mass quarantine where everyone stays at home. Before, sort of big examples in history from this disease with the plague and Black Death, where entire cities were shut off and everyone had to stay at home. So these are the potential methods for controlling it. So what then happened? So in China, how did they manage to control it? Well, there was no vaccines yet. There was no educational environmental changes which would be really made. But what they did was very quickly they had mass quarantines. So they had quick lockdowns as soon as they had cases. They had them very early, and that meant they only had to have them for short periods of time. Everyone was wearing masks, and because everyone was wearing masks, the transmission of the disease was slowed down dramatically. So even if they did have an outbreak somewhere, it didn't spread that quickly, so they could control them. And then what they had was they had very extensive contact tracing. So, and contact tracing with isolation. So they did it very quickly. They did it very deeply. So they really found all the contacts, and then they often found the contacts of the contacts. They used digital means from the beginning. So that was often, they would like keep track of where people had been, and anyone who'd been to that place was told to quarantine. And they were very strict. So people were carted off to isolation centres and quarantine centres where instead of being asked, please can you isolate at home. So a combination of those measures meant that they were able to control SARS-CoV-2 in China, and they did a very good job of doing it throughout 2020 and 2021. And they were relatively normal. Most people had a relatively normal life. It was only when Omicron came that they started to have the really severe problems. However, we had a problem in the West in that, well, our contact tracing is really being set up around STDs, and in general, the speed at which that needs to be done is not as quick. So while we do have extensive contact tracing within our public health authorities, it just wasn't designed to go at the speed which was required for to control SARS-CoV-2. And additionally, we have advice. I mean, being a democracy, we normally can only ask people to isolate. We can't tell them to isolate, and we certainly can't cut them off to a quarantine centre. So that's one big difference. So contact tracing, unfortunately, while it works well for many infections, didn't work for SARS-CoV-2 for this reason. In the beginning, no one really wore masks, and the reason for that was there was no direct scientific study at the time which should have done a controlled experiment showing that mask wearing was really important. And that was, I think, a big failing in the West, because SARS-CoV-2 is really very similar to SARS-CoV-1. There obviously are differences, but a lot of the way it's transmitted is very similar. And a lot of similarities, and very clear from what happened in Asia, they could get very good control using masks. So we failed to learn the lessons of what happened in Hong Kong and China and Japan. Border controls are very difficult in Europe because it's such an interconnected place. And quarantines in general are very difficult to do in a democracy. So consequently, our lockdowns occurred very late. And because they were very late, they had to be done for a very extended period of time, because things have got a long way out of control by the time they were implemented. Right. So that's the first bit about epidemiology. Where does epidemiological modeling come into it? And eventually where do computers come in? So epidemiological modeling is a combination of mathematical and statistical modeling, and uses a lot of computation. Now, by mathematical modeling, what I mean is a sort of mechanistic model. So if you think about a physics model or an engineering model, that's what people do in mathematical modeling of epidemiology, where you look at certain mechanisms and you build models of people or populations, how they interact, how disease spreads within them. And so these models are sort of mechanistic, and then what tends to be happening is, well, originally they were all pen and paper models, then they got more complicated, so computers were used to solve them. Well, these models tend to be just sort of calibrated with some parameters to try and fit those. The mechanistic model came first, the data came second. And the statistical modeling, which is kind of the other way around, where you look at data you've collected, and you want to sort of try and summarize that data, try and get some useful information out of all the data you collected about something going on within the process. And there you have a very, very simple model, which probably originally wouldn't be based upon mechanisms to try and summarize that data and get something useful out of that data. So you may be just looking at some average or something, or some regression, that type of thing. Again, computing was used there. However, what's happened now is, because we have so much computing power, these two things have merged. So the mathematical models now, because we have so much computing power, we can now look at the statistical properties of them by running these models hundreds of thousands of times. And with the statistical models, they now can be much more complex than what was originally were the original statistical models, and they can really look much more like mechanistic models now. So these sort of two sides of mathematical modeling and statistical modeling are slowly sort of merging together in being one. So one's becoming more statistical, and the other's becoming much more mechanistic. So what are we trying to understand in these modeling? What are the key things? So the first and probably most important thing that epidemiological modeling does is to try and understand the key characteristics of a epidemic. And there are three things which people are most interested in. And I think probably everyone knows the first one, which is the so-called reproduction number. So this is the R that everyone was talking about during COVID. That's essentially the number of people each person who's infected with it will go on to infect. Okay, so if R is greater than 1, more and more people are being infected. So you have a growing epidemic. R is less than 1, less people get infected on each generation. So you get a decreasing epidemic. To control an epidemic, what you need to do is get R below 1. How difficult it is to do is and how many measures you need to put in to control it is very much going to depend how much above 1 R is to begin with. I guess that's sort of the one that people most know about. The second thing, which is really important, is something called the generation time. And that's essentially how long it takes between one person being infected, how long from when they get infected to when they infect when they go and infect someone else. It's not really a single number, it's a distribution, but if you just sort of think about that sort of mean time. And that's really important for two reasons. If you combine the generation time and the reproduction number, it tells you how quickly an epidemic is going to grow. And the second thing is that generation time gives you the amount of time you have to intervene to prevent that person from infecting someone else. Okay, so if that is measured in months or years, you've got a lot of time to do things. That's measured in a few days. First wave of COVID-2, it was probably 5 days, and the second, and now we're Omicron, it's down to about 3 days. It's really difficult there, it's very short. This is one of the reasons why COVID was so hard to control. And the third thing is the so-called incubation time. That is the time between someone being infected and developing symptoms, developing the disease. And the sort of difference between the incubation time and generation time is very important, and it tells you it's also important for how you can control it. So if the incubation time is less, it means that people will not transmit the disease until they've developed symptoms, which makes it much easier to control because people can, in principle, know they have the disease prior to when they would normally infect other people. The problem with SARS-CoV-2, though, was actually the incubation time and generation time was about the same. So it means a lot of people were infecting other people before they had any symptoms at all. So it's much harder to control if you are transmitting an infection before you know you have the infection yourself. Obviously, you go back in history, HIV was very problematic as well for that reason, because there were zero symptoms often for like three to 4 years. And that was a big period when people could transmit the disease without having any idea at all that they had. So, so understanding an epidemic is one of the really crucial things which epidemiologists and epidemiological modeling is about. The second thing, and probably Now, the second most important, I would say, is sort of trying to understand what type of interventions are going to work. So I'll talk about digital contact tracing, but people will look at things like school closures and other measures. And understanding which one works depends really upon the characteristic of the epidemic, how it's transmitted. So these sort of three numbers: the reproduction number, the generation time, and the incubation time. Different measures will work depending upon those things. And the final thing models are used for are sort of a short-term forecasting. They get a lot of press, but it's probably in some ways the least important thing. I think the first two are the most important thing because it's about understanding what's going on and understanding what you can do. Right. So, computers. When do we use computers? Well, when we use computers, it all depends really upon depending on what type of models we're looking at. And I've sort of put things into 5 broad categories of different types of modeling and different types of places computers are used. And I'll sort of talk a little bit about how they're used. So the most simple models are things called compartmental models. And for those of you who are mathematicians, they're essentially groups of ordinary differential equations. And these have existed for hundreds of years, and engineers and physicists use them all the time. And there's 101 packages in MATLAB or Python, and things like that to solve them. So epidemiologists will just use all the standard packages for solving them, and they can be solved very quickly in a few seconds normally. Statistical models these days are really Bayesian models, and for sort of understanding and looking at the posterior distributions of models, people use an algorithm called MCMC. And again, this is really well studied. I mean, epidemiologists use it a lot, but we aren't the primary users. I think it's used across all different parts of science, and especially it's used in economics. And a lot of the sort of development of statistical models which we use really came out of economics originally. And then there are sort of things like standard packages called R, which I think most of the statistical community uses, and there's something called STAN, which is like a specialist thing for looking at these Bayesian models. And again, these models, they don't take a huge amount of time to run normally. A few seconds, at most, maybe a few hours, but it tends not to be that long. Obviously, there are some exceptions. We do a little bit of machine learning now, but again, I think this is dipping our feet into it, our toes into it a bit. They're using sort of a little bit using neural networks, a little bit using GANs and things like that. And then we would use all the standard packages there as well. However, I would say there's yet to be a problem in epidemiology where machine learning has sort of outdone standard traditional techniques. It's been as good, but I've never seen any problem as yet where it's actually done much better. But that could easily change. Then there are things called agent-based models, and this is what I'll talk a little bit more about. And this is what we were developing for looking at digital contact tracing. And what we do in these models is we essentially they really are getting down to the nitty-gritty details of modeling what's going on and how people interact. So the agents are individual people, and you will model like interactions of people, and you'll model how this disease moves between individual people, and then interventions can then be sort of applied very naturally to the agents in those models. These models, there's no standard way of doing them as such, and so people tend to code them in C or C++, but they tend to be bespoke software as opposed to having some generic platform. And depending on how big the models are, so if you're doing a small population or if you're trying to model like an entire country, the time it can take to run these models can run from a few seconds, but up to a few days. Where there's certainly worse models where people were modeling the entire UK. And so the model, in a digital model, they'll have a model for every single person within the country to try and model the spread of a disease there, or of an infection. However, the time when we use really huge amounts of computing power is when we do statistical inference on agent-based models. To do statistical inference on a model, on these mechanistic models, you end up using normally a technique called approximate Bayesian computation. Basically means you need to simulate the model tens of thousands of times, or even hundreds of thousands of times, depending exactly what you're looking at. So then you sort of suddenly go up to having things, these type of calculations can take from sort of days to like many years of computing time. So for example, there was one retrospective analysis I did, which was sort of looking at the spread of various different variants of SARS-CoV-2 around the UK. And in one weekend, I think I got through about 5 years of computing time on the test, because I was trying to do statistical inference in a large scale model, which sort of 5 billion agents. Right. So back to contact tracing. This is how traditional contact tracing works. On the first day, someone turns up at some healthcare provider and they've got some symptoms, and doctor or nurse will suspect it's a particular infection. And at that point, they'll potentially start treating them, but they'll run some tests to confirm that is the case. That can take probably an additional 2 to 3 days. Once they've been confirmed as a case, then it's passed to the contact tracers within the public health authority. And at that point, the contact tracer will contact this individual and arrange an interview. Again, it just takes a bit of time for this to happen, because essentially will be someone coming down, sitting down and spending 2 to 3 hours talking to the person to get a bunch of information, try and work out where that person either who that person potentially contracted the infection from and who they potentially could have spread it to already. Once that is done, the contact tracer then needs to go and talk to all these other people who have been potentially exposed to the infection as well. Again, that is all done manually. That all takes a lot of time. So quite often, between the case turning up at healthcare to the contacts being spoken to, probably like 10 days. If you add on the fact that it takes 4 or 5 days for people originally to develop symptoms for COVID originally, we're talking about 2 weeks after the time that they were infected, was before their contacts would be notified by contact tracing. And the problem with that is it's just too slow, because the generation time for SARS-CoV-2, I said before, was 5 days. You've got this 5-day window to do something in. If you find out, if you're not contacting if you're not getting in contact with people that are potentially exposed until 2 weeks later, there's kind of no point then, because it's already spread and it's gone on. So this was the problem with traditional contact tracing. So the idea of digital contact tracing is, can we speed this up? Can we shrink this down to be as quickly as possible and essentially use some form of technology to allow us to do the contact tracing part essentially instantaneously? So this is where it came about, and probably on your mobile phones had the NHS COVID app. And what the NHS COVID app was essentially was a UK implementation of digital contact tracing. And what it does essentially is it automatically keeps contacts of all the phones it's been in contact with for a certain period of time. And that means, and then once someone has tested positive, a message can be sent then to every phone that person has been in contact with to notify them that they've been potentially exposed, and that really speeds up this entire process of contact tracing. So that was the idea. So the problem was we need to do it very quickly because of the very short generation time. The idea was, can we use technology to do it much more quickly? So this idea was floated in sort of January, February 2020, and the government came and asked us a series of questions about could it work and under what conditions could it work. So things like how quick does testing need to be done? How quickly do you need to send your notifications? How much coverage in your population do you need? If there's no coverage at all, and if only 10% of people use it, is it worth having at all? Or is it just not worth having? If 50% of people have it, is it worth having it? So that type of question. And then the other thing was how compliant must people be? So if people knew that not everyone would if they were contacted would isolate if they had a message to isolate. But what would happen if 80% of people isolated or 60% of people isolated? At what point would it stop being effective? So these questions we were asked were all very detailed, and all very detailed around exactly about the exact mechanism by which the contact tracing would work, and how individuals would behave given messages. So that meant we were sort of pushed down the route of developing an agent-based model to try and answer these questions. The agent-based model is where you model all the individuals within a population. So to model an infectious disease, you have the individuals, but you also need to look at that interaction. So you have inter-interaction networks. Where do people meet? So the place where you're most exposed is always at home. And that's quite important. And place where a lot of the most infectious diseases will spread will be at home, because those are the people you have closest contact with. But then people go to school, people go to work, and then you meet sort of people randomly on the street and shops and things like that. So we had to model all these different types of interaction. And then once we were modeling the interactions between people, we could then model the interaction of the virus. So when people get infected, how likely you were to transmit the virus to someone, depending on how long you've been infected for. So when you were first infected with it, for the first few days, you would have very low viral load. You have a very small chance of transmitting it. By day 4 or 5, you would have very high viral load. You still wouldn't have symptoms, but you'd have a very strong chance of transmitting it. So we had to model that part, and then we had to model disease. And the key thing about SARS-CoV-2 was a very strong age structure within it. So it doesn't matter about young people getting it really, because they're going to have very few symptoms. Elderly people, it's very serious if they get it, because the chance of severe symptoms in the elderly is very high. And it certainly was very high back in 2020. Right. So we had a model of disease, and what we could then do, because it's an agent-based model, was we could get everyone, or not everyone, a subset of people, a phone with a digital contact tracing app, and we can model that digital contact tracing app. So we could model it when they came and they interacted, whether or not the phones had spoken to each other and had recorded those interactions. And we can model a lot of the other things that the government was interested in, things like the delay between people getting testing, sending out tests, getting test results back. And then we could model a whole bunch of sort of setups about what should happen once a positive message went out. Who do you send that message to, and what messages do you ask for? So, for example, do you tell people to stay at home? Do you tell people to just reduce their contacts? Do you say you should stay at home and actually your entire house should be quarantined as well? So we tested out all these different potential options, And we also tested out things like compliance rate. What happened if 80% of people did what was suggested? What happened if 60% of people did what was suggested? So that was the model we developed. Very quickly talk about the computational side of it. The core code was written in C, which you guys might think is a strange choice, given it's a very clearly an object-oriented thing. It was written in C for one of these reasons why things are often written in things. At the time, I had inherited a code working on a similar problem, and I was cleaning it up and extending it to answer a few more questions, and this came along. Because my mind was in how do you make models work in C for this, just a natural thing to go straight away. So it was kind of accidental choice because we had 2 weeks to get something working, and it was not you have 6 months to go away and write a model from scratch. It was like 2 weeks, needs to be done. So that choice was a choice of where I was, as opposed to sitting back and working out what would be best. The second thing we did with the model, which was quite important, was because C models are not particularly friendly for people to work with, is we from the beginning had an interface into Python and then soon added an interface into R. And this made it much easier for other people to interact with the model and to use the model because they were used to writing Python and R. And they're both very good packages for data analysis and data modeling. So if you want to integrate your model with sort of data modeling, it's quite important probably to interface it into the sort of languages that people who do data modeling want to use. Second thing, which we had from the beginning, was the fact it was open source, and it was developed by quite a few people. So we started developing it, but after 2 or 3 weeks, after the initial 2 weeks, we had it out on GitHub, had it open, and we've had 26 contributors now through various collaborations, and just other people joined, and we've had over 1,000 commits to the model. So it's been a sort of, not just been 1 or 2 people developing it, it's been a sort of collaboration from quite a few people. The other thing we did from the very beginning was we did a lot of testing. We did a lot of unit tests, and we did a lot of whole model tests, and they're run as regression tests. And I guess talking to a group of computer scientists, obviously you're going to say, of course you do this, everyone does this. Why would you do it? And it's clearly the correct thing to do. Unfortunately, a lot of academic models aren't like that, and they're not properly tested. And they're tested by the person who writes them by running it a few times and making sure they get the expected answer out. That's what I would say is a traditional thing. I think things are changing now, things are improving, and but with this model, we did from the beginning make sure it was very thoroughly tested, because it was very important we didn't make, it's very important we didn't make any mistakes. It's very important that you minimize the number of mistakes. I think that people who code and think there's 0 mistakes in their code have probably never written more than about 10 lines of code. So, but I mean, this was quite big. It was thousands of lines of code. So to minimize errors, you really have to test it as well as possible. So I think our model was a pretty good model. It was a very early model. But it was a reasonable one. Okay, there's definitely been better models since, and there's probably even by autumn 2020 there were probably better models. However, because our model was sort of open source and tested and documented and had friendly user interfaces, it meant other people could use it. So we got a lot of adoption. It was used by the NHS for doing a lot of their bed modeling. So I worked a lot with and still do with the NHS on that. Google used it as well, and finally the UK Health Security Agency are using it now. I just noticed I've been talking far too long. So at this point, I'll hand over to Adam, who is going to talk now about actually how the apps were developed.
Thanks. So I'm going to talk about Bluetooth headphones, amongst other things. So I'll try and be as quick as possible. There's an obligatory me slide. I had hair pre-COVID, honest. It was a very stressful situation. I'm actually 26. I've just had a very hard life. So I've had an interesting career working across kind of most industries. So I am a member of the British Computer Society. This is the first meeting I've been to since being a member in 2004. But I've been around quite a few places, worked across lots of different companies, normally on emerging problems that customers have got. So pretty much all my career has been, can you do this thing that your company's never thought is possible before? And as it turns out, that was quite useful. The reason I'm here today is not only because I'm now in Oxford working with Rob and Professor Reyes and everyone, but it's because at the time I got a phone call from the UK government saying get to London, and I was the lead architect for the UK COVID-19 app from March to June in 2020. So what I'm talking today is mostly about that period. I'll mention a few things afterwards because talking about the bad things, it's not great. So I'm going to give you some hope for the future at the end of the slides as well, if I get time. Main engineering challenges, some of these will be very familiar with you. Mythical man month. People think if we double the number of developers instantly, you did it twice as fast. It never happens, as we all know, but that's not a commonly known thing. I managed to create a team of 70 people across 4 continents. I was quite lucky in that our CEO, because I was working at Pivotal at the time, Pivotal Software, which was under the process of being bought by VMware. And Pat Gelsinger was our CEO at the time, is now the CEO of Intel. And he basically picked up the phone to me and said, take whatever you want. So I was like, I'm not going to take all 30,000 people, that'd be a bit excessive. Plus, it would be like herding cats. So I took 70 people across 4 continents. That was just our team. There was another probably 100 or so developers that were brought on through other companies within NHS X at the time. As designers, I brought in teams I trained at RAF and Army, and we worked with NCSC and other government agencies and other governments as well. So Singapore government, Norway, Germany, Ireland, some Canadian governments as well. So it's quite a lot that worked on. So that, coordination and people was a big thing. I think that's often overlooked in technical projects. Bluetooth Low Energy is the bane of my existence. I have unwittingly become a Bluetooth expert, not because I wanted to, because I had to. So I'll talk a little bit about that. Public cloud scalability. People think, well, it's a cloud, it just continues to scale. But as it turns out, they've not bought infinite amount of computers in those data centers. I'll talk to you about that. And then being led by the research. So obviously in agile software development, we try not to build a technology and then do square peg round hole into a solution. We actually talk to the people who've got the problem and then go, well, okay, let's figure out what the best way of answering that is. And that's what we did. That's why we worked with Oxford on it, rather than just say, hey, we've developed this great technology, now we're going to force you to use it. And then international operability, whilst creating something new, and whilst everybody else was creating something new, that was kind of hard to do. It never really happened. So my pandemic timeline, I'm not sure how well this build is going to work. So I get a phone call March 8th, developed a POC over 2 days, and then showed it. So this has not been seen outside of the NHS before. NHS Co-locate was its original name. This is why nobody lets me name anything anymore. I'm very bad at naming things, but I got a phone call on March 8th saying we need you to figure out a way of determining an approximate distance between 2 people who don't know each other using any device they've got on them. Can you do it? I was like, give me a couple of hours. So I jumped on the train, wrote half the code on the way down to London from Chesterfield. Tried different things, tried GPS, doesn't work in the city of London because there's too many big buildings. Being from Chesterfield, it's not a money problem. So we gave that up pretty quick and then looked at Bluetooth, and we were using Apple's Bluetooth beacon just for proof of concept. So we're saying quite high level just to figure out what is the art of the possible. And then this, which was a video, you would have seen it move. So down here, you would have seen that move from 1 meter to 1 to 3 meters to 3+ meters. And really what we were interested in is anything less than 8 meters. So that we built in a couple of days, and then they said, yep, come and work for us. So then we started off that project. So originally contracted for 2 months. Pivotal are not in the business of being an SI. So we go in, we pair with people in those organizations to build the first version of the app, and then we step away. That's always been our model. UK government wanted to extend until August. We said no. So we handed it over during May and then left the project in June. And then I slept for a month after that. But during that period was where most of the hard questions were answered. And this had never been done before. This was before Google and Apple released their stuff, right? So, you know, March 26th was the lockdown. We knew it was going to happen on March 11th, by the way. So, you know, we basically had 3 days to come up with something. And that's why it was never released early, because we knew we were going to lock down 3 weeks later. So we stopped developing something for immediate launch and started thinking about a full digital contact tracing solution. But there is another method that we could have used, which we're going to look at for future pandemics. And then we trialed that on the Isle of Wight. That was very successful. We actually found cases where that weren't found by manual contact tracing. So people who worked in the Tesco, somebody had caught it and passed it on to people because they wanted to go to work. And it passed it on to lots of people, and we found issues there. We also found other issues around interference with blood glucose monitors over Bluetooth. Who knew? But that was very interesting for that scenario. So this is a quote, who I won't name the particular government scientific advisor, but after saying this, you know, it shouldn't take you long. I had this risk assessment code run on my laptop in 30 minutes. It wasn't anybody from Oxford, by the way. So I sent everybody else out the room and had a one-way conversation with that person to make them realize that 60 million people walking around with up to 200,000 cases is probably going to be a bit more scale than a CSV file on his laptop. So, you know, but lots of people, you know, this very clever people don't necessarily know what it takes to build large systems. We kind of take it for granted in our industry, but we need to keep reminding people. But this was really a moon landing level of engineering effort. I'm not just saying that to make myself sound important, but it was really difficult because there was lots of unknowns. It's like, imagine Kennedy standing up and saying, we're going to go to the moon. We're not even in space yet, right? There was that type of thing. It's like build an accurate medical device using something that's designed to get your music from your phone to your car. That was effectively what we were asked to do. So this is me. This would have been better with a build. So this is me gallivanting around lovely fields at the start of the pandemic. Theresa May wasn't there. And I was using, the way we all used Bluetooth back then was just literally that. Get audio from your phone to your headphones into the car. That was pretty much it, right? Bluetooth had been around, Bluetooth Low Energy had been around for 8 years, Bluetooth much longer than that. During the pandemic, you saw this before. This is from, I think Luca was the main author on that paper, right? So Ferretti et al. That's the link if you want to go and look at it. And then this is Shodan behind here. So anybody, this is for the computer scientists who used to play lots of computer games when they were younger. And that was kind of my frazzled head all the way during the pandemic. And then once we finished the project, I was kind of, yeah, peace, love, and go back to a hippiness. And listening to music again. So that was kind of my pandemic. But Bluetooth Low Energy was designed, and you know, I as anybody who talks to me over a pint will know, I'm not very flattering when it comes to large tech companies who make mobile devices. But to be fair to them, it wasn't designed to ever be used for this. It was designed just to get some audio a few feet. And that's what their phones were designed to do. Just to use Bluetooth to do that, not use Bluetooth for all the possible things you could use Bluetooth for. And we often forget that. But that did mean that there was loads of issues. The great thing about standards, as we all know, is that everybody's got their own. Even in Bluetooth, the problem with a standard that's built by companies that pay for memberships for the standard body is that everything becomes optional and nothing becomes required. So even down to the size of the Bluetooth packet, how a write and a read works, how parallelization works and asynchronicity work is vastly different between Android and iOS, and even different versions of iOS. There's also different versions of Bluetooth, which have different additions and standards, different extra frequencies, which may penetrate walls better than other frequencies. So we had all those problems. And then we had the variation in operating systems. So on Android, one thing I didn't know is that the Android API is not sacrosanct. Each manufacturer can replace functions in the Android API with their own code. So on the same Samsung phone, for example, with the exact same model number, you buy a Samsung phone, say an S10 Lite. In the UK, it's likely to have a Snapdragon chip. In other parts of the world, it's likely to have an Exynos chip. They operate very, very differently, to the point where sometimes your protocol will work and sometimes it won't, just for a simple write. So we had all these type of problems, and there's hundreds and hundreds of them. I've got a website that lists them, so if you get really, sleep deprived one night, you can go and read about that. But then also we had, what were later claimed to be privacy restrictions in the operating systems, which we're not going to tell you the transmit power that your phone device that your app's running on is using. We're just not going to tell you, because you might be able to figure out, 1 meter more accurate how far that person is. If you're close enough to be within a meter, you can see the person, so it's not really a privacy thing. But what it is really useful for is, figuring out on a pathogen that spreads through sneezes, which go up to 8 meters, knowing whether it was 2 meters versus 4 meters is kind of important. So that would have been useful. So we had to work around all those things with different power settings and different versions of Bluetooth. So that was the first one. So my thing was, I was constantly for the first 2 weeks on the phone to Apple and Android and Samsung and everybody else and saying, I was this guy saying, I don't care what anything was designed to do, I care about what it can do. It's like, I understand it's not going to be the most accurate, the most reliable thing in the world. I can work around those problems. We've got lots of smart people that can write code. But I just want to know what it can do. And it was really, really hard to figure out. So we ended up with the Mobile Phone Manufacturing Association going to chambers like this one. So this is the National Physical Laboratory chamber. It looks like kind of an alien disco space, but it's not. This is basically a place where you can take a phone or another device in, and it prevents radiation from escaping and getting in. So you can test 2 phones and just look at the signals between those 2 phones. And there's nothing bouncing off the walls coming back at you, and there's nothing interfering. So we use this one in London, but the Mobile Phone Manufacturers Association did a fantastic job all over Europe. And they used loads of these chambers and tested 1,500 phones within a couple of months. So the idea was that we try and calibrate 2 phones to a known phone to kind of figure out what that is. Turns out calibrating something which changes on a log curve at 1 fixed distance is a really bad idea. But nobody kind of figured that one out at the time until afterwards. So, we worked with Fraunhofer in Germany, but Germany then abandoned the app, which means Fraunhofer wasn't funded, which means there was no further data or analysis on that stuff. And then the current calibration that's used today on the majority of contact tracing, be it the one that I maintain, the open source one, or be it the non or lesser open one, is still pretty weak. It's based on manufacturer or based on just the receive power, because we don't know the other half of that. But I'm kind of working on that as part of my degree. So this is, we got fed up with doing this at 1 distance. I was like, we need to do this at multiple distances. So I spent, after I finished on the UK app project, I then worked on an open source library thinking, we need to improve Bluetooth between mobile phones, whether it's for contact tracing or whatever, we need to go and do that. So I spent a nice long summer getting over my COVID experience of working on it by calibrating phones at different distances. I got fed up very quickly of doing this manually, right? So I created Colin, the calibration robot. And then we created another robot, which we never named, which was a bit of a downer. So Colin went along the floor, but then we found that different floor surfaces gave you different answers. So that was bad. So then we used a piece of string and some Lego. I kid you not, but it works really, really well. And we had 1 centimeter resolution, so we got over 8 million data points for different phones. And we figured out, MIT did a study where they put 2 phones at a fixed distance and took a signal strength reading over Bluetooth every minute. And they said, oh, you can't use Bluetooth for distance because it jumps around all the time. Well, if you sample something once a minute at 1 distance, how do you know that? So I said, let's not do that. Let's do it for many minutes and take thousands of readings at 1 centimeter resolution. This red line here is what Bluetooth does. And the reason for this, it's a bit of a weird interference pattern for anybody who's worked on radars or transmissions or mobile phone masts. And the reason for this is Bluetooth advertises every advert on 3 channels straight after each other. And those channels are not evenly spaced. And because of that non-even spacing, the interference pattern gives you something you can predict, which means that if you average it out over a few seconds, you end up with this green line. And that's very close to a linear model. So it turns out it is possible to do that. The only problem is, obviously for different phones and different signal strength, this could be moved up, translated up, because you've got a phone that you're seeing with a high transmit power. Or it could be that your phone's a worse model So this degradation drops quicker, so the angle of that slope's different. So that's what the problem is still, but you can get a pretty good approximation there. But we didn't know that at the time. This was only found out middle of 2020, and most of this data was generated 2020, 2021. Cloud engineering, the unseen challenge. This is a failed Antares launch. Nobody died in that one. But if you launch something and it blows up, people get a bit upset and they start to distrust things. So another European country, who shall name nameless, the team was promised a soft launch by the government. So they released the code and said to the ministers, hey, we've released it. And they went, oh, great, thanks. And then they immediately walked out of their building for lunch, encountered a report and went, hey, yeah, we just launched it. So naturally, you have millions of people go online to download the app. Now, downloading the app's not a problem because the app stores scale pretty well. But then registering that app and everybody hitting the registration service, which is that like on an AWS backend or something, and 8% of the country's population hitting that in 10 minutes is a bad thing, and it went down. All right. So because they were the first to launch and because it wasn't managed very well, that happened. And I was like, do I trust our politicians to not accidentally fail the soft launch? And my answer to that was unsurprisingly no. So we scaled the app backend to support 40 million people in 10 minutes downloading and launching the app. That requires a lot of testing. So we tested this daily for 2 months. We're able to do that because we're very, very good at platform engineering. But this did cause a few issues, especially in AWS builds. But this is the type of thing that people don't see. They see the pretty little app on a phone, but don't realize that, well, hang on a minute, if that's talking to every other phone, and then if there's a big outbreak and lots of people submit their contacts, and then we notify those contacts, we figured out that depending on the protocol you were using, how much data you were sharing, if you shared too much data, you could take down the UK's 4G system if there was too many cases in a day, which in a pandemic could happen. So we had those type of challenges as well. Cloud engineering issues. One thing I will say, anybody who works at Microsoft or knows anything from Microsoft, there was 2 companies that turned up on Wednesday, March 10th and said, whatever you want, you can have it. We'll worry about the cost later. Those 2 companies were Pivotal VMware and Microsoft. So this isn't a dig at Microsoft, right? They turned up and they said, whatever we'll do will help. The only problem is, when everybody was sent home, little Johnny and little Johnny's sister then wanted to use Teams to talk to their teacher. Well, they probably didn't want to, but their teachers wanted them to go on it, right? Turns out you can't prioritize customers on Azure, or you couldn't at the time. What that meant was the entire country jumping on Teams meant that all the dynamic capacity for scale out was taken up by Teams. So Ministry of Defence, NHS, and ourselves using the NHS account, basically when we tried to stand up a new VM, it failed routinely for weeks upon weeks. So we could use the servers we'd already got, but we couldn't stand up new ones. Now, when you're doing platform engineering and updating things on a daily basis, so not just pushing the software out, but pushing new container environments out, you need to kill and start containers all the time because you treat everything as cattle instead of pets. So you take a shotgun to it rather than, oh yeah, we'll update you and there's new software, just kill it, right? Because we were doing far too much agile, that meant we killed a lot of VMs and we needed new ones. And because the capacity ran out, we couldn't do it. So Microsoft tried to build out a new area in Azure UK. But the problem was, because everybody in China was ill, shipping new components to the UK to build these servers was a bit of a problem. So they tried everything, like they were shipping stuff all over just to try and make this work, but they couldn't do it in a way that scaled enough. So what we ended up doing was moving to AWS because we were on a containerized environment at the time, Cloud Foundry, if you're doing it to Kubernetes, but at the time Kubernetes wasn't mature enough. If you're doing on Cloud Foundry, we were able to take the same scripts, deploy it to AWS, and then switch over the development environment without the developers being interrupted. And we did that in 24 hours from the order to switch. You wouldn't have been able to do that if you were not being a very agile, very good platform as a service offering. So people often overlook software to help developers do their job easier. The only way we were able to switch cloud environments was because we had that abstraction. We weren't using native Azure or native AWS and then having to switch between the two. So yeah, one of the lessons is don't go native. And then scale. RabbitMQ, the largest civilian messaging system in the world. Does anybody know what it is? There's a trick question. I do know the answer. It's NHS England's backend. So all the different NHS apps like Choose and Book, and when you get sent your SMS from your doctor's surgery or whatever, that all goes through different apps connected to the same RabbitMQ backbone. And so because RabbitMQ was supported by Pivotal, we decided to use that. It's also used in a lot of defense environments because it is reliable messaging rather than lossy messaging. We decided to use SQL Server because we wanted a trusted database. Now, I wrote NoSQL for Dummies, but I was not going to use some of those databases for this. So one of the things was, I was like, I need this scale. And Microsoft went, look, you need the biggest SQL server that we've ever built. You need 5 nodes of it. I was like, cool, let's go do that. Turns out we burn $1.5 million a week on data. But that was necessary because of the amount of load testing we were doing. So it sounds insane amount, but when you do it as a percentage of GDP, it's not actually that much. And the limiting factor we had, weirdly, was scaling the monitoring and the load test layers to push enough load through it like a real launch would have. And then security is the responsibility of everybody. I've worked in a lot of secure environments. So the mobile app and the infrastructure, the back end is regarded as critical national infrastructure. It made the list. I was like, oh, on that list, that's quite nice. And then I went, no, actually, that's really bad because I have to go in lots more meetings. So we had, red team exercises, external consultants, NCSC doing interesting things, lots of penetration testing, lots of manual security reviews, layers upon layers of encryption, more than you would do on a normal web service. And then anonymous, not anonymized identifiers. So we weren't taking people's information and anonymizing it, because any of us that have worked in the insurance industry knows that that doesn't work. We anonymize it. So we created an anonymous identifier that was unique to each installation that never left the phone. So nobody could identify that, not the mobile phone companies, not the networks, not the UK government. So we went through lots of chats because of that, NHS Digital, Cabinet Office, Information Commissioner's Office to make them understand what technology is. And then, okay, great. So now you're anonymous. But when you go to a test center because you feel quite ill, we need that result to go back in the app and match against what is now an anonymous set of contacts, so we can notify your next contact. So we're like, damn it, we now need an identifier. So what I ended up doing was writing some software that generated a non-anonymous identifier that had a time to live. So the system that generated that, it would just kill it after a fixed period of time, or kill it as soon as the test result came back, whether it's positive or negative. So that identifier only lived until the test result arrived. As soon as the test result arrived, it was removed, because that was enough to give us the information as to who to notify. So that's the way we did it. And that system was still in the later app, and it's still used today. That's not a bad way of doing things. And then Bluetooth as well, rotating MAC addresses. So Bluetooth privacy, Bluetooth energy privacy mandates rotating the MAC addresses are approximately 15 minutes. Obviously, you need a bit of jitter, otherwise it's really obvious which one's the new one. But on iPhones, turns out, and we found this out by using an RF10, that when your phone's locked and the screen's off, and then you lift it up and the screen comes on and shows you the time, that changes the Bluetooth signal on iPhones. And then when you put it down again, the screen goes off, changes back. If it's locked or unlocked, it changes. And that's all in the manufacturer area on every advertisement. What Apple phones also do is before they switch MAC addresses, it's not random. They give a hint as to what the next MAC address is going to be over a encoded format, not encrypted, which was broken by INRIA in France at the start of 2019 and published at the start of 2020. And that's still a weakness that's today. So you can track an iPhone for up to 2.5 hours. Didn't know that. Nobody knew that until the start of this project. Then, so we handed over to NHSX and preferred partner, which we've been working with since the start. and then they decided to move to the Google Apple system because some other European countries had already started doing it. Not going to go into that. And then I slept for a month, kind of recovered, grew a few more hairs back, and then started working on an open source Bluetooth reliability layer. And that ended up being used in Australia and Alberta, Canada's apps. So it was on 7.6 million phones at its height. And the interesting thing about Australia was it's a federal system. So the parts of Australia that used the data, because they didn't have to use the data, obviously, those that did use the data had a really good figures for lack of spread. So there's even one case where somebody flew into Australia in Sydney, somehow infected a member of staff at the hotel. That member of staff went in a taxi. Those two people didn't know each other, and then got off in a particular nightclub area of Sydney, went out that night amongst 200 people where they only need 2 of them, and then went home. Now, that could have caused a massive outbreak, but because the majority of people had that app on their device, there was 200 contacts that could have only been found through digital contact tracing that were found in that one case. Now, in Australia, you'll see some news stories that say, oh, only so many 100 contacts were contacted through digital contact tracing. That's only so many 100 that were not also manually contact traced. Because there were so low cases in Australia, because of the controls they had there, manual contact tracing found the people eventually, but digital contact tracing found them first. Yeah, but digital contact tracing still did a better job. So that's quite an interesting finding. Singapore government as well, we're using an open source layer. So there's quite a lot of talk amongst the teams internationally about how to do this. So I've been working with Singapore for years, and they donated their open trace code to the Herald project, which is currently still part of Linux Foundation Public Health, so it's all Apache 2 licensed, and we're using that to build other stuff as well. And then we won an Open UK award in 2021, but it's still being onward developed. So this was done for one country, or half of one country, I suppose, because Northern Ireland and Scotland did their own thing. And this is the only current project, be it Apple or Google based or OpenTrace based or any other protocol based, that's still being onward developed. Everything else stopped being developed at the end of 2021. So the idea is that this is looking forward to prevention. So Adam's wanting from histories. So, we'll do the bad stuff before we do the good stuff. There was a nice happy slide at the end. But lessons we should all learn from: there is no performance for high performing agile teams that are already formed. If you can't bring them in, teach them how to work together using a very agile process, lastminute.com. So even if you've got an SI that's huge, they're still going to have to form those teams. So it just doesn't work. Contracting out to large agencies doesn't work. It's very, very costly for very relatively poor skills and knowledge. I'm quite an agile purist because I worked at Pivotal. I don't believe in certificates saying I'm a Scrum Master that are any good. I don't believe in SAFe, and this is very much my own belief. But any of the development outfits I knew that didn't do very, very agile work would just not have been able to deliver during something that stressful. One thing I would say is launch then improve. We need to get government more comfortable with launching a very basic product and adding to it over time, rather than thinking they're building a bridge across the Forth estuary where you can't use it until day one and then it's done. That's not how software works. They still need to understand that they need to be an intelligent customer. They need their own techies, and they need to release stuff quickly, get feedback. And we need to treat healthcare IT systems and insurance policy. There's probably lots of tales during the pandemic of things being fixed. So there was no kind of automatic system for pulling in test results from all the different regional test centers. That's been solved. It was an Excel spreadsheet. Do you remember the story about the Excel spreadsheet? There's a limit in Excel spreadsheets. There was too many cases being tested, and therefore they lost loads of test results. That wasn't my team. That was somebody else, but I do know exactly who that was. And they were absolutely distraught by it. But yeah, because it was it was used to, as Rob was saying earlier, it was used for things like sexually transmitted diseases where you don't have hundreds of thousands of cases a week, you have a few. So yeah, that was fine. But now you've got something that spreads very, very quickly. It needs to be a live system. So we really need to invest in that as a country and internationally as well. And then trust and consent are paramount. If you build an app that only gives somebody bad news, they will not have a positive view of that app. The digital contact tracing apps, all of them, in retrospect, either didn't tell you anything, which is a bit disconcerting, or told you were about to fall ill and die, basically, you know, from a simplistic point of view. But that's basically what they told you. Now, I don't know about you, if I've got an app that, you know, if I had a weight loss app that told me I was fat all the time, probably not going to help me lose weight. Right? If it said, oh, you can do this, Adam, go for a run, then I'd ignore it. But at least I'd be more positively inclined to use the app, right? So that's one thing. You know, we do need apps to give people information to prove that they're working. And there was some internal work done in the nudge unit at the Cabinet Office that showed that if any app could prove it was working. So, for example, if it showed you how much you were mixing one day and you went, oh yeah, that scores basically how much mixing I've done this week. Yes, I trust that data. Then when it asked you to self-isolate, it's be like, well, it looks accurate, so I should probably do that. Figured out you were twice as likely to adhere to the advice, but we never ended up adding that in the app. And apps need to give benefits, not bad news. These opinions are my own. They're nothing to do with the University of Oxford or my former or current employers. But big tech doesn't know best. Democracy is the worst form of government, as we all know, except for all the others. But democracy has the benefit that I can vote out my MPs when they suck at managing pandemics. Can't vote out the CEO of Google, Apple, or anybody else. Companies that are public listed companies are formed for shareholder value. And I'm not a kind of left-wing person at all, but that, you know, compensation drives behavior. I've worked in sales for years. So you've got to be a bit careful about that. Trying to get technology to fit into a medical system doesn't work. You need to do it the other way around. You need to find out what the problem is and do it that way around. So you do need to talk to experts. You can trust epidemiologists. And rather than decide what the right answer is, you need to think, well, how can we, you know, slice parts of the problem off and get better and better over time? And yeah, last point is we need to consider how happy we are about the NHS or any tech company data mining or selling access to our data via their platforms to unknown organizations with unknowable research ethics controls. Centralized healthcare databases are not a good thing. So have a think about that. What some of the stuff I'm doing in part of my PhD is fully distributing as much as possible of these risk assessments. So having them run on a wearable, you know, really small in-memory model running here, so that all my data's here, it's running here, I can see the results here, and then I only talk to the health service when I need to. You know, I need to be able to control my own risk, so I need the data on my phone. So that's what we should be doing. So yeah, just be very careful about that. Now, as computer scientists, we're probably more familiar with the danger because we're very good at writing code and linking data together. We're probably more aware of the dangers than most other people, so we need to continue to warn them. But there's always hope. I told you I'd end with a happy slide. Lots of work has been done and continues to be done worldwide. So obviously in Oxford, I have to do a bit of a shout out because we're here. And there is it's been thought about for a while, but there's a new Pandemic Sciences Institute, PSI. There's different research groups going into that. One of them is the one that we're in, which is looking at epidemiology. I think the vaccines one's in there as well, and one around, I think you'd probably call it delivering healthcare in the community, looking at how you put controls into the community as well. So, you know, there is lots of work being done in peacetime, thinking about, you know, COVID-25 or COVID-26, or that comes on. And because the work on COVID passes, instead of getting a little bit of paper when I want to go to an interesting country and have my tetanus jab, you can now do that digitally on your phone. So that's one benefit. So, you know, the vaccine pass that you had in the NHS app for when you travel internationally because you've been vaccinated, that same technology is now being applied to all vaccinations worldwide through the WHO. That's quite a benefit because it makes it a lot easier to travel internationally. And application creators are now more focused on individual control and consent and access to people's own data and on looking at decentralized approaches than they were ever beforehand. Before, it's like, I'm going to create an app, I'm going to put something on a public cloud and then send all my data there. Whereas now everyone's like, ooh, this has raised a bit of an issue. We need to think more about things on people's phones, things being stored centrally but encrypted so only that person can get them. So it's completely switched around how application creators think about those things as well. That's the end of my thing. Shout out for the talks I've given or can give as well, because I don't shut up very often. So yeah, I do quite a lot of this talk. I've given it the RAF before as well. Autism and ADHD under pressure because I'm autistic. I've got severe ADHD as well. So yeah, there's lots of good going on. So we'll be a bit more prepared next time. But if you know any MPs, tell them to invest, especially the Pandemic Sciences Institute in Oxford. But thank you very much, and we've run out of time massively. But I don't know if there's any questions for either of us.
Thank you very much. Any questions, thoughts, comments?
Question for both, really. If the pandemic had happened 5 years earlier, would we have been able to do all this?
Ooh. Don't know about the modelling side. What do you think?
I think we could have done the modelling side. I think that would have been fine. I think had it happened 5 years previously, we would have been in serious trouble. Because a lot of the because of the vaccine, a lot of the technology for the vaccine was really being developed over that time period. A lot of it came out of the work being done for Ebola, which was 2014, wasn't it? But those things were just coming forward at that point. So 5 years earlier, it would have been much different because all these technologies were far less well developed at that point on the vaccine side. I think on the epidemiological modelling, that would have been
Your very long computer runs would have taken 10 times longer.
Yeah.
it's true, but I think for the question that we needed to answer in the beginning, it was fine. So there weren't the longest computer runs I was talking about were things actually I did later. Looking back on these, for many of these key questions, actually quite simple models work quite well.
In terms of mobile apps and the backends for that, we only got the speed of development possible because everything was highly automated in a containerized environment, even though it wasn't Kubernetes. But containerization, 5 years, 2015, it would have taken at least twice as long to build any of that. Bluetooth Low Energy was on all the phones still. So since kind of 2012, pretty much every phone in Western countries has had Bluetooth Low Energy on it. So it would have been okay there. But I think the main issue would have been uplinks. It would have been 3G back then. So the amount of data sent over the wire about who'd fallen ill and the contacts they'd had would have taken down the mobile phone network. And yeah, processing on the back end would have just been so much longer to write the code and get it up there. It wouldn't have been fully automated and containerized, I don't think. So I think it'd have been, the nightmare scenario would have been if it happened 5 years ago and we didn't have. So the only reason the Oxford AstraZeneca vaccine came so quickly is because they already had the kind of basis platform there. The nightmare scenario would have been 5 years earlier without a ready to go kind of vaccine testbed, because you'd have been there 2 years. So yeah, that would have been a nightmare. Hopefully next time we'll have all this ready. We won't have to go into national lockdown. We'll just have to download an app and manage our own risk because we'll have the data to do it. And then if we do need to use an app to do digital contact tracing, we'll just be able to download it and have it running within 2 hours. And that's what the open source project that I do, which is totally nothing to do with Oxford, to keep them separate. But that open source project aims to have the ability to add a configuration file and launch a digital contact tracing system within hours. It's not there yet. We've got the mobile layer, but we need to add the other layers on top, but we're working on it. So if you've got any spare time and want to contribute to an open source project, let me know, because we're always desperate for developers.
So Rob, you mentioned or praised the efficiency, I suppose, and success of the contact tracing that was used in China. And I was just wondering whether that was as a result of the fact that it was either mandated or there was pre-existing surveillance technology that enabled that, or they were just used to done it because they've done it before and we haven't.
I don't know the details. I think they were already had the surveillance technology there for. I think my word for praise is probably not quite right.
Yeah.
I was just saying why it could work there. I'm not saying we should have done the same. I'm just saying why, and spying on their own people obviously is something which happens a lot in China. So I think they were pretty ready to go on that side of things. It's the first thing, and then I think the second thing is they can mandate things much more than so. If the government says if you get notified, or we see that you are a potential risk, we are going to take you to a quarantine centre, and there's nothing we can do about it. It's just a different country. So
It has flared up again recently, though, hasn't it, in China? When we let the lid off of it.
Well, that's why.
I mean, I think what's happened in China was we're talking about the reproduction number R. So let's say the original strains of SARS-CoV-2, the R was about 3. And the basic R on a naive population interacting normally. Probably by the time we got to Delta, it was around 5. First strains of Omicron, we were probably up at 8, 9. The latest strains of Omicron, we won't be on 10. So the problems, that would be on a naive population. Now, here, we're not a naive population. We've all been vaccinated. We've all had it as well as being vaccinated. So it's very different. In China, most of the population was still immune. So most of the population was still naive. So no one had ever had COVID. They had been vaccinated, but not even like the over 70s. I think it was not. I mean, the coverage was all sort of 70-80%. I think as opposed to 98%, 95, 96% in this country for people over the age of 70. So it was a very naive. And I say not naive, I'm talking about naive to the infection population. So therefore, the task of preventing it spreading was getting harder and harder and harder and harder as each new variant came out, and it just got to the point where what they were doing was just not going to be possible to do. I mean, I think the Chinese would have had to give up sometime. They tried really hard, and I think that their problem was that they didn't say, right, over the period of 2 months, this is our plan to sort of go from where we are now to sort of going back to some much more normal interaction. So they sort of clicked overnight. It's like there's all these prevention, all these measures in place, and then overnight they just stopped them. And that was the reason why it increased so dramatically so quickly. They sort of had this sort of complete switch, as opposed to had they done a sort of 2-3 month phase, I think things could have gone much better. But they're now, and they will be now getting back to normal with like the rest of us. And COVID will be something which will be going on, and it will be in the background, and there will be people in hospital with it. But it's sort of the levels are now a sort of manageable level, as opposed to what was happening back in 2020, where the health systems all around the world were on the point of collapse.
Yeah, I think one important thing to remember is as well that when it comes to what controls we build into software to allow people to collect data or to respond to something, the correct answer is different in every country. because you've got a different appetite and a different trust of the health system and a trust of the government in different countries. And I think one of the lessons was most large tech companies are based in Southern California. They have a very American-centric view of what's acceptable. Whereas in Europe, we have more public healthcare. So we trust the NHS a bit more, or we did do, I don't know about now, but yeah, we certainly did do at the time. So, you know, this idea that privacy is a binary is incorrect. Individual people, like I won't install TikTok. You ask any 14-year-old, they'll install TikTok, right? Well, it gives data that enables China to do machine learning to further subjugate their people, right? So we each have to make our own decision. Each country has to make their own decisions. I think one thing we do have to remember is when we build open source projects, we give a flexibility of choice of controls and choice of accuracy, and then trust in democracy to control what those governments do. Now, some governments are a bit more trustworthy than others, but we can't be the world's police. So that's one thing I would say.
My question, I think, has partially been answered. It's primarily, I'm just trying to get a feel for COVID going forward. Is it literally just going forward inside like another flu? What?
I don't know. I asked almost the exact question to Neil Ferguson about a week ago. That's confusing, and because he's far more knowledgeable than I am, I'll give his answer. We just don't know.
Yeah,
It's quite likely it's going to end up being something like flu, where there'll be multiple strains and it will just keep them going, but at a quite low level. However, we can't get ruled out that it will just get to an evolutionary end, and it will just, it's just not known at the moment. I think most people are going thinking it's going to always be here now.
yeah.
And yeah.
Okay.
But
You've
but I
given me a
say,
pretty good idea with your answers. Just
yeah, I just, yeah.
last few statements.
I mean, we could be very unlucky. I mean, there still is a chance that the severity of it could get worse again. We should be lucky if we moved into a point where the level of severity has gone down a lot, even if it was on someone who was naive. But it's also, we have pretty good immunity via vaccines, and we've all had, we probably all had Omicron, I expect.
Yeah.
It'd be very difficult to most people to avoid it, but I think a lot of people had it without realizing it because of the vaccine, and things were less.
I've been astounded that I've never tested positive. I entered into one of the research things from London. So I've been tested 20 and 30 times probably, and I've never tested positive, which is, so in theory, I've never had it.
Oh, wow.
Depends
on the test, right?
It's possible, but I think figure is 2% of the population have it at any one time.
Really? Yeah.
And it's really quite.
It's been there.
It's just it's still there in the background, but it's just we've got a point where people are not falling particularly ill from it.
Yes.
It's gonna. But anyway, I don't think anyone has any definitive answer. I mean, the year which has just gone, I think we've had 5 waves of Omicron. I think we're currently on our 5th one from the first one of different variants coming. And what we've seen is there's been one variant, and just as it starts to fall, a different variant comes and takes over. And we've just seen wave after wave after wave of the virus mutating. And what we've been lucky is every single time the symptoms haven't been getting worse. There's been no real change in how severe the disease has been, which has been good because Delta was really quite a lot worse than the original strain. And Omicron now is probably less severe than the original strain. And we've all been vaccinated.
I've got a techie question for Adam.
Yeah.
I'm asking you to put your agile hat on,
Oh, gone.
but mainly focus on the specific solution. You mentioned that endless testing just delays, so I'm referring to that bullet point on the slide.
Yeah.
So when you're
Whereas more endlessly talking about whether it should be a 13-point or a 14-point fault that delayed it. But yeah.
but when you're dealing with an end customer or a government, what techniques are you finding useful to actually reach that approach the panacea of fast turnaround and prototyping?
Yeah, I think the best way of doing this is to pick a problem in that organization that is naturally agile itself. So when I trained the first developers in the Royal Air Force on the agile method we were using in Pivotal, which came in really handy because when we needed lots of phones testing, I could pick up the phone call and get the RF to do it, which was great. But when we started teaching them, they were like, yeah, but why do we need that agile? We can just contract for it. It's like, yeah, but if there was ever a conflict where you were having to integrate with somebody that wasn't in NATO, you would have to build that code on the fly. So how are you going to do that? Because you can't contract that out and take 6 months and then the process. And they went, yeah, that could happen. Yeah, that could happen. And then they did it. And the really interesting thing is, Ukraine's happened, and their reservist agile development team were able to take off-the-shelf drones and build a NATO-compatible intelligence system within 2 weeks. So that's the type of thing. So I'd say pick a problem that is naturally agile in that customer.
And convert the customer.
Convert the customer. The only way you're going to get it working, you can't just make the development team agile. You've got to make the business unit agile, and that's the hardest bit. Development teams get taught agile at university now, not very well, but they do get taught it. But you can't just do agile development and have everything else waterfall. That's wagile, and it doesn't work.
Yeah.
All right, you need the problems coming in. You need those people talking to developers with a balanced team of developers and product designers and product managers, not project managers. And only with that balanced team, with direct talking to the customers and the people who know what they're talking about, is the only way to build agile software very quickly. So like we got, like I say, the POC, which was, as you saw, a very shoddy UI because I did it. That was done in a couple of days, but we had a basic digital contract chasing app up and running in 2 weeks. Now, if you contract that out, well, they tried and everybody was taking ages to do the contract. So it just doesn't work. So I'd say that's the way to do it. The problem you've got in government is they outsource all the IT, or most departments do. Some departments have started bringing it back in. So if you look at Department for Work and Pensions, they're bringing all their devs back in. Yeah. MOJ with their agile software factory in Sheffield is a really good place. If you ever get a chance, go and have a look at that place. And then RAF, Royal Navy, and to a lesser extent the Army have all got agile software development shops now. And the RAF one's very interesting. It's down the road at Benson. It's just moved there. It's the Appivate team, and they do build mobile apps. And there's a code club on every RAF base, so they can scratch their own itches. And then if they get a decent app, they get the central team to make it look nicer and be secure, and then they roll it out. So, you know, it is possible, but it took me 3 years to do that with one customer in the RAF. So it's a long, long road.
Yeah.
Can I ask a silly question?
There are no silly questions.
It probably only works in an ideal world, but if some pathogen comes along and you can isolate everybody that's got it, it doesn't get transmitted, and therefore does it not just die out? So would that not be the way to attack this problem, or is it because of the timescales involved that it doesn't work?
I mean, that's obviously what China was trying to do, and we just live in a very interconnected world, yeah. So it's effectively unless you can get that in the very, very beginning, possible to do,
The rabbits out of the hat sort of
Yeah.
thing. Or what have you.
Well, and they thought it was pneumonia, right? They thought it was a weird type of pneumonia at the start. So if it was a disease that made your eyeballs bleed and fall out, they'd be like, oh, that's obviously novel. But with something that, just looks kind of like the flu or kind of like something else, that means it's more time until they realise it's something different. So
I mean, the other thing is, Wuhan is a city of 11 million people.
Right.
So it's not like it came about in Oxford,
No.
yeah.
and it's a small place.
Yeah.
It's
Yeah.
Huge question.
it's a very big place, so it's
Yeah, of all the places it could have started.
Yeah. Sorry.
Just in terms of like the research done and sort of the lessons learned over the pandemic, were there really any sort of fundamental changes to the field of epidemiology through this, or is it still sort of being done more or less the same way as it was being done before?
Good one. That's why I get to sell my default subject.
so. I mean, suddenly a lot of people became epidemiologists overnight. That was one thing which happened. What has happened which has changed? Hard for me to say. I would say I started working in epidemiology in January 2020. So I started working on HIV then, and so I was not very experienced when I started. It was hard to tell you anything about before and afterwards. But I think one thing which has changed, I think, looking overall, is people now appreciate looking at genetics much more. So prior to COVID, the idea of looking at viral genetic evolution was a sort of subject which some people were looking at, and the group we worked with in Oxford were one of the few people in the world really looking at it a lot, but it was considered by the community to be something a little bit strange. Why would you do that? You don't need to know about that. You're not going to learn anything useful there. And as we now know, sequencing the virus has been one of the key tools in sort of understanding the spread and understanding when new variants come about. And was obviously, it was very pivotal when it came to developing the vaccines, developing tests and things like that. So I think probably, if we look at epidemiology overall, one of the big changes now is people now really realize genetics of the virus is really important and is a really useful tool to understand what's going on. I'm not saying that didn't exist before. I'm just saying it's now just become a much more it's now mainstream as opposed to being this is something which some people look at.
I think OpenABM existing as well, and because now it exists, it could potentially be used for decision support in the future, right? Like
I think sort of, so OpenABM, I think one thing, I don't know whether this will actually be a permanent thing. So OpenABM are agent-based model, but also there was one was developed at a similar time in Seattle, yes, which has actually gone on to be a much bigger thing, and they have a big group of people still working on it. But both of these things were doing modeling at a standard which was not previously done from a coding point of view in everything. So I have a background in working in the industry, working in the financial industry, where we do a lot of modeling, and actually financial models and epidemiological models really aren't that different. And working in the finance industry, there's a lot of standards you have to have with code, and all code is highly tested and all models are highly tested, and you have to make sure that your output, your model is doing what you think it should be doing. And that type of thing was the reason we went at OpenABM. We took that approach for OpenABM, but other people are doing this now, and I think that is going to become the standard that people do, which is done by the people in those other areas and have been done for a long time. I suspect when people have their big blue models, etc. in the future, they're all going to be less than that standard. They're all going to be, at least the code is going to be properly open source, even if it's not open source development.
Yeah.
So I imagine there will be that change. I said, I think sort of it goes across all academic subjects, and different academic subjects have done this prior to it, and done it at different points, and they convert. I think it's just as writing complex models become a much more important thing in each field, the need for properly testing and the right tests has just become much more important. And just depending on what line different areas are, depends on how advanced they are along that line. But I think epidemiology has now moved to that point where I'm sure there's loads of disciplines previously where the molecular biology simulation, I'm sure, would have been doing all this before. I knew big physiological simulations before where people were doing this 15 years ago. So I think things are changing, and I just think it all depends on the people and the subject. But
Yeah, and pandemic response as well. I think look at the WHO flu plan. There's very little mention of consumer digital devices, even though there's been a massive explosion in the amount of people using them, especially wearables. But then you talk to a lot of doctorate students in Oxford, especially in medicine, and they're like, oh yeah, I'm looking at monitoring people to spot when they develop this disease or symptoms for this thing. And it's like, well, hang on a minute, everyone's kind of developing these risk models that could run on a wearable. So I think that's one thing that in future, for health generally, as well as pandemic response, is really good news, in that there's lots of work going on standardizing those platforms, and lots of people that want to build risk models that take, you know, outputs from the simulations that are done centrally and then shrink them down so they can be run on an individual basis. And I think that's quite exciting.
Yeah.
Not just from a pandemic point of view, but, you know, all diseases, I think.
I think I was listening properly when you were talking about the 8-meter Bluetooth.
Yes.
Was that a limitation of Bluetooth as a technology, or was it specified from a medical perspective, as if you were 9 meters away from someone, you weren't going to catch COVID?
It's a limitation of your sneezing ability. So there was a study done mid-2020, maybe early 2020, that figured out how far a sneeze went. Now, obviously, there's different ways things can be transmitted. But I think the original risk, I don't know, the risk model in the UK app, there was a kind of exponential drop off in the risk with distance. So up to 1 meter, with, you know, from 5 centimeters to 1 meter, it's basically the same. And then after that, there was a kind of an exponential drop off in the risk. So for 5 minutes at 1 meter is very different from the 5 minutes at 3 meters, for example. I think that's where it came from. So I think the vast, like most of the risk, like 76% of the risk is likely to be within 3 meters or something. I can't remember the exact number. There's a large amount. Well, that's what we thought originally anyway. I think there may or may not be a publication about to be released that shows time is actually the most important factor. Time of exposure rather than distance.
Forgive my ignorance, but so with kind of phone, therefore, let's say I've got a phone, I've got a contact out, you've got it there.
Yep.
Can my phone know how far away you are from this? So we can then say, well, actually, don't worry about him.
Yeah, so can it do today in the contact tracing apps? It does not do it that accurately. However, as part of what I'm doing, this is why I get to sell my DPhil. Part of what I'm doing in my DPhil was I was looking at self-calibration models. So we're never going to have, we're not using Bluetooth to create a digital tape measure. It's not going to be centimeter accurate, but we don't need it to be. Because even if you were able to calibrate a phone model that accurately, everybody's got a different case on their phone. Everybody stores it in a different pocket, in a different rotation. So it's not that helpful. So one of the things I've been looking at, and I've not written it up in a good enough format to publish yet, is a way of doing self-calibration. And based on the tests I've done, it looks like you can just collect on a phone just other devices you've seen, which are identified as mobile phones rather than Apple TVs. And you can self-calibrate that phone within a couple of days worth of walking about. And by doing that, all of a sudden you get a bit more accurate, so that it's never going to be exactly the same. So like if you and me stood shoulder to shoulder for the whole day and walked around, we wouldn't have exactly the same number. But you know, like your step counter, if you went on a walk with somebody, it's about 10% out, even though you've done the same amount of steps roughly. You probably get that level of accuracy, and that may be good enough depending on what you need. But that's assuming that distance is the big risk factor. You know, next time it might not be. One of the questions that was asked quite a lot was, can we tell when people are inside or outside? Because if they're having close contacts in a park in fresh air at 2 meters, that might be very different from being stuck in a very small room with them at 2 meters for the same period of time. Now you can't do that on a mobile phone because it's in my pocket, but on a wearable, you know, on the open source project, we designed a wearable that was a unit price of $15 that could do Bluetooth and light sensor, and you can run a machine learning model to determine whether you're indoors or outdoors based on light frequency. So that's the type of thing that if we investigate that now and look at the capabilities of the things around us, not what it was designed for, but what it could do, then we would know how accurate each input that could be to a risk algorithm. And once that pathogen is understood a bit more as to what behaviors give you the most risk, you know how accurate the result of that, you know, formula is going to be within the risk score. So it's about being prepared, I think.
I believe the indoor-outdoor thing can be done on a standard phone via the microphone.
That's true.
However, just by listening.
So can distance, actually.
So you can just hear the types of sound, and I think Google are able, if they turn on your microphone, to tell you whether you're indoors or out. However, it was not done because it's considered a complete no-no as far as privacy is concerned, for very good reasons. But it's sort of, in principle, could have been done, but in practice, no one went near it because of the implications of it. Turning on people's microphones and listening.
Yeah, that was
Even
used.
if it's just for doing completely innocently doing, which would have been done, it's still just considered to be too much. And this is one of the big things. I think a lot of things in the apps were made as private as possible because ultimately one of the key things is how many people take them up. And by making it as private as possible, you will get more people to uptake to have it. And by having more people to have it, it's far better and it's imperfect and less good. If more people have it, then to do something a bit better, but less people have it.
Have you got any questions from the?
Actually,
No,
we
no.
don't have any questions.
Nothing at all. No?
What we have here, I will pass that on. Thanks to the speakers, there's a number of resounding, thank you very much for fascinating talk. Somebody's hoping PSI will make us more ready next time.
So do we.
Big vote.
Talk to your MPs.
Oh, I'll bring it to a close then, if there's no more questions, and just say thank you very much for essentially echo what Jeff just said. Were extremely interesting talk, and the two, if you like, windows into the development was eye-opening. Thank you very much.
Thanks.